So thank you everyone for coming. My name is Mariana and I'm the program manager for Clause. And today I'm joined by Cesar, our software lead, Drew, the CMCC lead, and Delenn, our outreach chair. And we'll be talking about how Clause, the collaborative lab for advancing work in space, is bringing innovative software technology to human space exploration. So just some brief background on us. We're a multidisciplinary group of graduate and undergraduate students, and our goal is to create human-centered, software-driven application to further humanity's presence in space. And our team members come from various disciplines, including the School of Information, Electrical Engineering and Computer Science, Aerospace Engineering, and Climate and Space Sciences. Our team was founded in 2018, and in terms of our projects, we work on software, hardware, as well as user interface and user experience. And aside from that, we host outreach events in collaboration with CEDS and also technical sessions for members to learn new skills. Currently, Clause is working on a suite of software to help astronauts who go on extracurricular activity. And our components include an augmented reality, voice assistant, central web server, and also user interface and user experience design. And our various components are meant to be run concurrently to give the user a seamless experience. First, I'll be talking about the augmented reality component, which is Atlas. So Atlas is the AR toolkit for lunar astronauts and scientists, which was built and developed on the Microsoft HoloLens. In the images on the bottom, you can see what a user would see when they put on the HoloLens. So on the left, the user can see a small map, their current task, their biometrics information, as well as Vega, which is our conversational AI part. And on the right is an example of how a user would add a waypoint at their current location. So Atlas's goal is to improve the efficiency and independence of astronauts while they're on an EVA. And this works well with Vega and CMCC, which are additional sub-projects that we'll talk about later. And some functionalities include sample collection, field notes, navigation and waypoint marking, mission tasks, biometrics and warnings, as well as the QR scanner so that an astronaut can quickly scan an item to learn more about it. And next, we'll hear from Delenn about Vega.
Hi, I'm Delenn Bauer, and I'm going to talk about the voice entity for guiding astronauts, one of the facets of the Clause software suite. One of the main projects Clause has been working on this past year is the voice entity for guiding astronauts, or more commonly referred to as Vega. Vega is a conversational AI voice assistant with the goal of aiding astronauts on EVAs as a component to augment our software suite. For reference, conversational AI software is software that allows virtual assistants to complete tasks, hold natural conversations with people, and retrieve information hands-free and in real time. More common everyday examples include Apple Siri and Amazon's Alexa. Vega is built upon the open source Rasa platform and is context-aware, which differentiates it from general use case voice assistants such as Siri. Vega is intended for use specifically with respect to space exploration, meaning that it won't be able to tell you the gas station that is closest to you, but has a variety of more space exploration specific features. The motivation behind Vega is that astronauts wear cumbersome suits and often need both hands free to complete mission tasks. An interactive voice assistant can help them efficiently and effectively obtain any information they need and assist in performing tasks. Vega also initially proposed as a way to interface with the Atlas system. As briefly mentioned in the last slide, Vega is built on a conversational AI platform called Rasa. Rasa is a powerful open source platform that is Python and markup based, as well as being extremely customizable with various packages and options, and therefore a good tool for us to build our own conversational AI. It allows us to define the flow of a user through various use cases in the form of stories, allows API calls, and takes sample input data to classify input via very effective machine learning models. The current features that we've been implementing in Vega are in regards to providing the status on biometrics and suit supplies, such as information about heart rate, oxygen levels, suit pressure, etc. Allowing inquiry on upcoming tasks and navigation has been another focus this year, with implementing capabilities of locating certain landmarks and objects and providing information concerning those, as well as directing the user and astronaut to those places if they wish or need to go there to complete a mission. On the right is a state diagram depicting how Vega handles some of these requests. We have also been working on integrating Vega into other CLAWS projects and services such as the CMCC, which we will explain in more detail later. So how does Vega work behind the scenes to provide an astronaut with the desired information and formulate the necessary response? The astronaut first supplies a voice command such as, "What is my heart rate?" which is then converted from speech to text. Through machine learning and training, Vega attempts to determine the intent of the user, in this case, a biometric request concerning the astronaut's heart rate. Vega then acts on the intent and gets the information necessary and processes the request by making an external call to the CMCC. Vega determines what information is useful, in this case, deciding that it needs to ask the CMCC for biometric data, and converts that back into info that is useful for the specific request. In other cases, Vega might need to ask the CMCC to create a waypoint for a specific location or more navigationally oriented voice commands. Vega then responds to the user with the relevant information, converting the text back to speech along the way. Here's an example conversation that exhibits some of Vega's functionality. Vega can provide details on a variety of biometric data such as heart rate, oxygen level, and suit pressure. It also handles a variety of functionality in terms of navigation to certain waypoints. For example, here, if the astronaut wanted to make an inquiry regarding the location of nearby craters for a specific mission, they could ask, "What craters are within 5 miles of my position?" in response to which Vega would determine the nearby craters by sending a request to the CMCC and processing the data to provide the desired information to the user. If the astronaut needed to go to Cone Crater for their mission, they could request directions to the location and Vega could start navigation to the crater. This is just one sample of what a conversation with Vega would look like, and it can handle a variety of these sorts of situations, and hopefully we will have the capability of handling more features in the future.
Hi, my name is Drew Vanderspool, and I'm going to talk about the CLAWS Mission Control Center. So the CMCC is a Python web server we built using Django, and its purpose is to support and tie in all the other software components we've been talking about today to support astronauts on EVAs. So its three main functions are providing graphical user interfaces for the Mission Control Center, providing API endpoints for other software components, and providing database storage for EVA-related data and information. On the left, we listed out some of the tools and packages we used, and on the right is a screenshot of the early version of the landing page. The first component of the CMCC is its graphical user interfaces. So while the astronauts are out on EVAs, Mission Control Center needs a way to view and interact with important data in real time. So far, we've built out several different views to do this on the CMCC. On the left is our map view, where Mission Control Center can view points of interest, astronaut locations, habitat locations, and potential hazards. And Mission Control Center can create, edit, and otherwise interact with this data in real time, which allows them to advise astronauts with a full view of all the possible points of interest. Currently, we're building this with the Bing Map API, but hopefully in the future, there will be a similar tool to generate map imagery for the moon instead of here on Earth. On the right, we have an example of our notes view, where Mission Control can view notes in real time created by astronauts. And with this feature, Mission Control can also edit and provide additional technical annotations to the astronauts' notes. Other views we've built out include viewing biometric data, important vitals with the astronauts, and habitat and room data. The CMCC also provides a simulated stream of suit data. So a simulation can be ran where a user can manually trigger something like an oxygen leak. And then you can test out if other components of the software, such as Vega, detect the drop in oxygen and successfully alert the user. The second component of the CMCC is its API endpoints. So these endpoints provide a means of communication between the CMCC and its database and all the other software components. And the name of the game here is standardizing the data communication between all the components. So instead of having to build a complex network where each component has to be able to talk to all the other components, each component only needs to be able to get and send information with the CMCC. So in this example diagram, we have a Vega user requesting waypoint data for Yost Arena, which I guess is on the moon now. And Vega sends a formulated request to the CMCC, and the CMCC responds with a standardized response. And that's the same type of response something like Atlas would get or any other project using the CMCC. And this allows for expansion and future projects to easily be interactive with the data without creating a whole new complex communication network. Other API endpoints we have built and are live on the CMCC include Waypoint Creation, directions request using Bing Map APIs, biometric information retrieval, which is what the endpoint Vega used in Delenn's example on the previous slide, habitat information like internal pressures and internal temperatures, and much more, including the simulated suit data I talked about on the last slide. The final component of the CMCC we'll talk about today is its database, which provides storage for all the information we've been talking about. And again, like on the previous slide, the most important thing here is standardizing the formats and storage of the data. And when we were initially building out Vega and Atlas, everything was individually storing their own waypoints in different ways. So slightly different types of categories and slightly different possible ranges of values. And this makes communication exponentially more complex and opens the door to errors. Whereas now that we're doing everything through the CMCC database, we have a central place to store all this data in a standardized way. And this ensures that all of our software components are getting access to accurate, consistent data. The diagram on this slide is waypoint creation. So waypoints can be created in several different ways, either through mission control using the CMCC or through an astronaut using Vega and Atlas. And then those waypoints can be viewed from mission control with the map view or by the astronauts, again, using Atlas with Vega. Beyond waypoints, the CMCC is also equipped to store things like field nodes and sample data, the biometric information, room and habitat data, and much more both now and in the future. So that wraps up the CMCC, and I'll pass it over to Cesar.
Hey everyone, I'll be giving a short overview of the UI design on Claws. So just as important as a software is a UI UX design, and we're very lucky to have a great team of designers on Claws as well. And so their main focus this year was on improving the design of Atlas. So everything was done in the realm of augmented reality. And more specifically, they decided to focus on the camera, notebook, and navigation functionalities. And so their overarching goal of the system was to basically enhance astronaut safety and operational efficiency on EVAs. And so their design also emphasized autonomy and self-sufficiency of the astronaut. And so what you can see along the bottom of the slide here are different mock-ups of various menus within the Atlas interface. And so the picture in the middle is a screenshot of a mock-up that was taken on HoloLens, so you can get an idea of what the user sees while wearing the device. And finally, on the right side, you can see an example of paper prototyping, which is where individual components of the UI are printed out and mounted physically so that the designers could actually see the interface and move things around in real time. And so with these various designs in place, we have a really strong starting point for software development on Atlas in the future. None of us here on the panel are on the design team. So if you have any more questions about their design process, definitely feel free to reach out to their email, claws@uiux@us.edu for any more details. And so I'll just wrap up by showing up what we have planned for the future, aside from continuing development on Atlas, Vega, and the CMCC. So one tool we began pursuing this year and will also continue to work on in the future is called Trek. And this will be a collaboration between us and the NASA JPL Trek team. And so basically Trek, we want it to be a VR application, which is kind of a step away from the AR that we've usually been doing. And its purpose is to allow the user to view areas and terrains on the moon, along with any related data overlays. And so examples of different areas that the user could look at can include landing sites for rovers and also like Artemis missions. And the idea is that once the user selects some area to view, you can then add on different data layers, such as rock detections, crater detections, slopes, lighting, etc. And this tool will be really useful for people like mission planners, scientists, engineers, both before and after missions. And so what you see on the bottom of the slide here is just a GIF of what we're envisioning this to look like. We didn't make this. This is called Mars VR from JPL, but we're hoping to either adapt it or create something similar, but just for the moon. And another thing we've wanted to pursue is to incorporate machine learning into not just conversation, like through Vega, but also into our biometrics. And so we can apply machine learning to model resource depletion on the fly during a mission. And so, for example, if water is decreasing at a rate that's not nominal, that can be indicated and alerted to the astronaut and mission control.
So I just wanted to give a quick thank you to our supporters, especially Dr. Leah Sterling, who's been our faculty advisor. And thank you all for coming. Let us know if you have any questions, and feel free to check out our website or email us for more information.
Thank you, Claus. Appreciate having you back this year to talk about your progress. It's good to see that even though with the pandemic, you've been able to make progress on all of the projects. So if anybody has questions for Claus, feel free to send them in the chat.
Mm-hmm.
I think we've got about 10 minutes for Q&A.
Yeah, I wanted to start off with a question. So you work with, a lot of different NASA centers. I know you're working with NASA JPL for the Trek project. So what is it like to have those sponsorships or those relationships, and how often do you meet with them, and what do those look like?
Yeah, I think we can all say that's really amazing to have all those different connections. As both of you know, because you've been on Claus too. It's really amazing whenever we can have a chance to talk to different people from different NASA centers. Like ever since the start of Claus, we've been pretty connected. First with Houston, and then NASA Stennis for when our collaboration with Bliss, and now JPL. So it's really awesome to be able to just hear from experts in the industry and just ask them questions, and also sometimes have them ask us questions about our project. It's really awesome to just have that back and forth.
Yeah, a lot of the times when we were on Claus, it was we're designing a video game and it's going to look really sci-fi and futuristic. And a lot of people at NASA are I don't know anything about it.
I don't know what you're talking
about.
about.
So it's up to the young people to kind of come up with new ideas. So yeah,
it's very cool. And it's very different too. I think that's one thing that I think I took out of Claus, is that this kind of thing is very new. NASA is not really they're starting to look into this, but as you said, it's a lot of, they want the young folks tackling this. So it's very neat. And I hope that progress still keeps going strong, even through the summer and fall.
Yeah, and also as you talk to these people, they're real people in the industry, and so it definitely gives you the sense that what you're working on can have an actual impact, which is pretty cool as well.
We're just going to wait a minute or so to see if there's any other questions, if anybody can think of anything. Otherwise, they can direct questions to the Slack later to follow up with you.
Yeah, thanks for having us here.
You're always welcome.
Always a pleasure.
All right, so we'll go ahead and move into
wait.
Oh, we've got a question. Okay, Gus asks, for Trek, will you be working with code from JPL's Marv's VR program, or will you be designing it mostly by Claus?
That's a good question. So we our idea has changed a lot over the course of this past semester, and so we originally wanted to kind of get like their Mars VR code, which we did. They shared like their GitHub with us, and basically poke around and see how we can just modify it to basically change it to Moon VR. So that's one avenue, but another avenue is, you know, just going completely from scratch and just, I guess, like taking inspiration from Mars VR and seeing how they did it. But yeah, I guess like which avenue we're going to go down in the future is to be determined.
All right. Thanks for that answer.